The trigger goes on the stack. You see their hand, 5 cards, face down. Do they have it? Will it flip? We've solved this puzzle from the Delver player's perspective, computing natural flips and brainstorm flips, with perfect hand knowledge. But Magic isn't played with perfect information. Welcome to Part 3, the final chapter of our mathematical journey into Delver of Secrets. If you missed Parts 1 and 2, they are linked in the description. Part 1 covered the natural flip, pure probability based on decomposition. Part 2 explored the brainstorm flip, how manipulation transforms chances into certainty. Now we are answering the ultimate question. What if you don't know whether they have brainstorm at all? This is the opponent's reality, the incomplete information scenario, and the math can solve it. Let's close the loop. When Delver's triggered ability goes on the stack, the opponent faces a fundamental uncertainty. They can see their hand size, 5 cards, maybe 6. They can count the visible spells in the graveyard and on the battlefield, but they cannot see what's in their hand. From the opponent's point of view, the game branches into 2 possibilities. Branch 1. Brainstorm is not in hand. In this case, the flip is purely natural. It depends entirely on whether the top card of the library is a spell. We already know this formula from Part 1. Using only visible information, the expected natural flip is the quotient between remaining spells and remaining cards. This is the baseline probability, what happens when there is no manipulation. Branch 2. Brainstorm is in hand. Here, everything changes. As we saw in Part 2, if they have Brainstorm, they can just cast it in response. If they have another spell in hand, the flip is guaranteed. If Brainstorm is their only spell, they still have a 90% plus chance of flipping it by drawing into 1. This is the Brainstorm flip probability we computed in the previous video, accounting for both cases. The question is, how do we weight these 2 branches? We need to determine the probability that they actually have Brainstorm, and then to combine both scenarios into one answer. This is where the Bayesian probability tree comes in, one final time. To compute the total expected probability flip, we use the law of total probability. We take each branch, multiply it by its weight, the probability of being in that branch, and then add them together. Each of these 4 factors can be computed using the tools we've built. The probability of having no brainstorm in hand comes from the hypergeometric distribution, sampling from the remaining deck. The probability of having at least one brainstorm is just the complement. The natural flip probability is the formula from Part 1, and the brainstorm flip probability is the complete formula from Part 2. When we substitute all these values and compute, we get a single comprehensive formula. Yes, it's dense. It's layered with binomial coefficients and with conditional probabilities. But here is what matters. It only uses visible information. Visible spells, visible known spells, hand size, deck composition. The opponent can compute this without knowing the hand. Let's plug in the numbers for the most iconic scenario. Turn 2 on the play. The snapshot is described by the following parameters: 60 card deck, 32 spells, 4 brainstorms. Delver cast on turn 1, 5 cards in hand, 53 in the library, and no spell visible yet, only Delver and a land are visible. Using the comprehensive formula from above with these parameters, we get that the expected flip probability is 69%. On the play, from the opponent's perspective, Delver flips roughly 7 out of 10 times on turn 2. To validate this, we ran a Monte Carlo simulation, 1 million games of this configuration, each randomly dealing cards and checking if Delver would flip. The result, 69.19%. The theory matches reality, the math holds. Now let's adjust for being on the draw. The differences are 6 cards in hand instead of 5, because of 1 extra draw, and 52 cards in library instead of 53. This slightly changes the probabilities. The total expected flip is now 72%. Again, we confirmed with Monte Carlo simulation, 71.60%. The extra card drawn increases the chance of having brainstorm, pushing the total flip probability slightly higher. Let's summarize everything we've built across this 3 parts project. We've derived the complete formulas for computing Delver's flip probability from both perspectives. In detail, from the player's perspective, the natural flip is 51 to 61%, depending on spells in hand. The brainstorm flip is from 93 to 100%, is nearly guaranteed. From the opponent's perspective, the expected natural flip is about 55%. The expected brainstorm flip is 99%. And the total expected flip is 70%. That 70% is the number that matters for strategic decisions. Should you hold up removal? Should you tap out? Should you raise? Assume Delver flips, because it doesn't flip every time, but it flips most of the time. And that reliability is what makes Delver one of the most dominant creatures in Magic history. Magic is a game where decisions matter, but the best decisions are built on solid foundations. When you understand the probabilities, you stop hoping and start knowing. You don't wonder if Delver will flip, you calculate whether it will. And when you are staring down that turn to trigger, you will remember, Delver doesn't flip because of luck, Delver flips because of numbers, and now you know those numbers. Thank you for following this journey through all three parts. We went from basic probability ratios to conditional distributions to full Bayesian analysis, turning suspense into certainty and uncertainty into precision. Parts 1 and 2 are linked in the description if you want to revisit the foundations. If you enjoyed this deep dive into the mathematics of Magic, let me know what mechanic or interaction you'd like to see analyzed next, because every card tells a story, and behind every story there is always math waiting to be uncovered. Now, go play with confidence, because when Delver triggers, you are not watching magic happen, you are watching math unfold.